Okay, we're going to give you about 5 minutes to do the warm-up. Do numbers 1, 2, and 3 on page 25. We'll pause the video here for you to do that, and then we will go over the answers together. So when it says, what's the complement, we're going to do 1 minus 0.78 and get 0.22. The relationship between A and not A, or the probability of A and not A, is if you add them together, you get 1. So now if you look at number 3, we have information about this credit card company. So the probability of a long-term cardholder is 0.42. The probability of paying in your bill full is 0.35. And the probability of the overlap or the intersection is 0.23. So if you put that on your Venn diagram, 0.23 goes here in the middle. The entire circle of L is 0.42. So we have to do a little bit of subtraction. This is for the L. We get 0.19. And then for F, the entire circle of F is 0.35. We get 12%. So now we're going to use those values to calculate C and D. Okay, so the probability of L given F. When it's a given, you're limiting the circle you can look at, just like you're limiting a row or a column in a table. So for L given F, we're only going to look at the F circle. So the entire F circle has 0.35 or 35%. Now the part that includes L is just the 0.23, so that's your numerator. If you divide them in your calculator, we get 0.66. We can do the same thing with F given L. That means we're only going to look at the L circle. So your denominator is 0.42. Now again, the only part that contains F there is the 0.23. So if you divide, we get 55%. So now, are F and L independent? You have to mathematically show that they would be independent or not independent. So we have two choices. You can either show that the probability of F is either equal or not equal, so we're going to say question mark, to the probability of F given L, or you can show the probability of L, it may be equal or not equal to the probability of L given F. Either one will work. If they're not equal, they are not independent. If they are equal, they would be independent. So we have back up in part A, let's see if I can get it all on the screen. There we go. The probability of F is 0.35. We found the probability of F given L was 0.55. They're not equal. You could do the same thing the other option, 0.42 and 0.66, not equal. So F and L are not independent. You have to show this math with these numbers to prove the independence or not independence every time. Okay, so go ahead and do all of number 4. You can do that. We'll pause the video here and give you 2 to 3 minutes. So your answer for A is that P, the probability of A given B, means the probability that a room has a king-size bed given that it has a view of town square. So filling in our thousands table, thousand is our total. They give us the king-size bed is 620. And they give us the view is 430, excuse me, and the king-size bed and a view is 380. And now using subtraction, you can fill in all the other cells. And now we can use that to calculate B given A. So the probability, of A given B. So the denominator is going to be 430. That comes from your row of B. And then the numerator is 380. And if you found a percent, that's 88.4%. So now if we go to write a general rule for any A and B, let's think about the values we got here. The 380 and the 430. If I wanted to write other fractions that would reduce to the 380 over 430, we could make a denominator on both of the 1,000. So like if we did 380 over 1,000 and 430 over 1,000, that would simplify because we multiply by the reciprocal of the denominator, and the 1,000s would cancel. And we get what we wanted. So what is that 380 out of 1,000? So this cell is the probability of A and B out of the whole chart. And then this probability for the 430 is just the probability of B. So the general rule that this equals the probability of any A given B is you can do the intersection divided by the probability of B. Okay, so it says suppose that A and B are independent events. If we know that A and B, if you know probability of A and the probability of B, can we determine the probability of A and B? So let's write what we know about conditional probability. If they're independent events, the probability of A given B will equal the probability of A. Now, going back to the definition we just wrote on the prior page, we said that the probability of A given B is the probability of A and B all over the probability of B. So if we look at these two steps, the same probability equals two different things. So we can set them equal to each other. And now as a last step, to simplify, if I just want probability of A and B by itself, we can multiply both sides by the probability of B. and get the probability of A times the probability of B. So now we're going to use this. This is another I'll just say definition that we can use now to calculate some probabilities. So let's try number 2. We're rolling a 6-sided number cube, like a dice, and flipping a coin. So if we have, for A, probability of A and B, well, first we have to think, is the dice and the coin, are they independent or not independent? They're going to be independent. Your dice and your coin have no effect on each other. So we can use that the probability of A and B is equal to the probability of A times the probability of B. So what is the chances of getting a 4? It's going to be 1 out of 6. And the chance of getting a tails is 1 out of 2. So our probability is 1/12. We already kind of just answered B. Will probability A and B be the same as the multiplication? Yes, because they're independent events. A and B are independent. So now if we think about part C and D, you have a bag of marbles, and if we pull one marble out and not put it back, that's the key thing here. We're going to place it in front of us. We don't put it back in the bag. We have dependent events. The second marble depends on what you pulled the first time. It's not independent. So to calculate C, the probability of C and D, well, okay, so the probability of getting a blue marble on your first draw is going to be 2 out of 5. But your probability of getting a blue marble on the second draw, there's only one blue marble left out of 4 marbles total. So that's 2 out of 20. So for part D, that's not going to be the same as the probability of C times the probability of D. Because the probability of C, we said was 2 out of 5. And now the probability of D is getting a second blue marble. So that would be, you can do the probability of getting a blue and then a blue, or the probability of getting a red and then a blue. So the probability of D, which is the second blue, is this second blue. So we have to calculate the probability of getting a blue first, which is 2 out of 5, and then getting a second blue would be the 1 out of 4, plus now the probability of getting a red is 3 out of 5, and then getting a blue is 2 out of 4. 2 out of 4. So if we calculate these probabilities, we get 2 out of 20 plus 6 out of 20, which is 8 out of 20. So then if we answer the question, is C and D the same as C times D? So is 2/5 times 8 out of 20 the same thing as 2 out of 20? And they're not going to be equal. Okay, so let's talk about 3A. We have the dice again with 1 through 6 and our coin with heads and tails. So the dice is rolled and the coin is flipped. Will they be independent? Okay, How do we know? We could just say, yes, they're independent because the outcome of the dice will not affect the outcome of the coin, or we can mathematically show it. So let's say we want to show that the probability of getting a 6 is equal to the probability of getting a 6 given that we had a heads, for example. So the probability of getting a 6 on your dice is 1 out of 6. The probability of 6 getting a heads is the probability of 6 and heads out of just the heads. So if we think of our sample space, all of these are the outcomes. So the probability of getting a 6 given we got a heads is 1 out of 6. Because since it's only given heads, you can only look at these outcomes, and there's 6 of them. They're equal, so it's independent. If we toss a coin 5 times, what is the probability we see a head on all 5 tosses? So the probability of all 5 heads, we know it's independent, so the probability of getting the first head is a half. So the probability of getting another head is a half. And if we toss it 5 times, each time the probability is a half. So if we multiply these up, we get 1 out of 32. So if you roll a cube 3 times, or the dice 3 times, what's the probability it shows all 4s? Well, the probability of getting a 4 is 1/6. My next roll, I'll have the same probability of getting a 6 and a 6 for my 3 different rolls. That's 1 out of 216. All right, last but not least, for number 4. So they're giving us the probability that a customer pays the bill in full, the probability that they make regular online purchases, and the key part here, the 2 events are independent. So what's the probability that we pay in full and make, I'll say O for online purchases? Because they're independent, we can multiply the 2 probabilities and get 29.5%. So we're going to do one little extension since we're honors. Page 32 in your packet is blank, so if you want to turn there and copy this down, we're going to do a little algebraic proof. And we want to show, since we know that probability of A given B equals probability of A, can we then show that the probability of B given A equals B, probability of B? So let's start with what we know. We know that the probability of A given B is the probability of A. That's our given. We saw earlier, we can rewrite this conditional probability as the probability of A and B all over the probability of B. And if we manipulate that around, we can multiply the probability of B to the right side here and get the probability of A and B is the probability of A times the probability of B. Now, if you think about an intersection for the and, is the probability of A and B the same thing as the probability of B and A? Okay, I hope you thought to yourself that yes, we can say that that order doesn't matter. So now we've got the probability of B and A is equal to the probability of A times the probability of B. looking at where we want to go, I want probability of B by itself. So let's divide both sides by the probability of A. And then as a very last step, we can rewrite this term back as our conditional probability, and we proved it. Okay, so for your homework, you're going to do pages 29 and 30. The key thing for doing the questions on page 29 is I highly recommend making a two-way table from the Venn diagrams. If you look at your answers on Edline later, we made a two-way table to be able to answer all these probability questions. It makes it so much easier.